So we are making progress. We have moved up the protocol stack. So we are now at the transport layer. So we are going to look at different attacks possible at this layer as well as solutions to the same. So what is the role of the transport layer? And what are the transport layer protocols you are aware of? So that is right. The role of the transport layer is process-to-process delivery. We have seen earlier that at a given host, at the user space, you can have many processes running. For example, one process can belong to the web browser, one can belong to the email client, and so on. And when packets come, the role of the transport layer is to deliver it to the right process. So this is a minimum functionality any transport layer protocol has to do. But sometimes some transport layer protocols also enhance the best effort network layer service model to meet application expectations. What I mean by this is, for example, the email application as well as the browser application, both of them want reliability. It is possible that you could implement them as part of these processes themselves, that is application layer processes, but then you have to implement this for each and every application. So instead, if you implement it at the transport layer, all of these applications that want reliability can make use of it. That way you don't have to implement it at the application layer. So that is what it means. So among the protocols, UDP, TCP are very popular at the transport layer. There are other transport layer protocols as well. UDP provides what I mentioned here, this simple multiplexing, demultiplexing service. Whereas TCP, which is more complex, not only provides demultiplexing, that is demultiplexing is directing the packets to the right process, it also provides reliability, congestion flow control. So in this video, we will focus on TCP since it's the most popular transport layer protocol. So here is the TCP header. So there is a source port, destination port. Basically, this is used to direct it to the right process. There is also sequence number acknowledgement. These are all used to provide reliability. This is used for flow control. And there is a checksum also to do some integrity check, but this is not cryptographically secure. This is just to ensure that there are no errors in the packet. One thing you should note is any TCP connection is identified by this 4 tuple where the source port, destination port come from the TCP header, whereas source IP and destination IP come from the network layer header. Even if one value within this changes, that means it is a different TCP connection. All this you should know by now. This is just a high level recap. So how are connections opened? How many messages are exchanged to open a TCP connection? Right, this is the famous 3-way TCP handshake. So you have a SYN packet that is saying let's synchronize, and you select a sequence number as part of this packet X. This X is often random, Y, we will get to it shortly. And in return to this other side, so A wants to initiate a connection to B, so it is sending a SYN packet as well as a random sequence number it chose. And in response to this, B will also say, okay, I also want to synchronize with you, and it will acknowledge this SYN, and it will also choose another random number Y. Notice that this acknowledgement is basically saying, fine, I received X, I want X plus 1. That is what this acknowledgement means. And in response to this packet, A will ACK this packet, and thereby the ACK is I want Y plus 1 because it is sending Y, this is Y plus 1. And in this packet, you can potentially pack in data and send to the other side. Now the question of why do we choose a random sequence, initial sequence number? There are 2 reasons for this. What are they? So one reason is you don't want segments from different connections to get mixed up. So let me tell what I mean by this. Suppose there is a TCP connection 1 Let's say all of them start with sequence number 0. So it's kind of sending sequence number 0. That other guy also is sending sequence number 0. And something happened and you send sequence number 32. That other guy also is sending maybe sequence number 12. And so on. So this corresponds to X. This corresponds to Y. Why this difference? Because maybe X sent more data than Y. And let's say you close this particular connection. And this packet somehow is still hanging out in the internet because routers can delay packets. Right after this connection, let's say they started another TCP connection and again did this 00 and then maybe they are now at 11 and this packet from the past now comes to A. In which case there is a danger that it may consider this as part of this connection because the sequence number belongs in this space. That is one reason why you want sequence numbers to be randomly chosen so that you can easily distinguish between the different connections. So for example here, if the sequence number was some number like this, and here when it is progressing, maybe you chose some number like this, this will not fit within the window of sequence numbers that A is expecting. If you remember, TCP is a window-based protocols. At any given time, it expects sequence numbers only within a window. Anything that doesn't fall within the window, it will drop. So this will not fall in the window, thereby it is going to get dropped. So that's the basic idea here. There is also another reason why this is done. This is for security reasons. If these sequence numbers are predictable, you can spoof and hijack. How? We will see shortly. So that is with respect to opening a connection. How many messages are involved for closing a connection between A and B? Assume that you want to close the connection both ways. That is right. You will have 4 packets exchanged for closing a connection where 2 packets will close the connection from one side. So example here, this is A is telling I want to close a connection and B is acknowledging. After this, B can continue to send data. It's just that when A says I will close a connection, it is saying I don't want to send any data. So data from A to B is no longer permitted, but B can continue to send data. Whenever B is done, B can then send a FIN and A will acknowledge it, and this will close the connection from B to A, in which case B also cannot send any more data. So this is how the TCP connections are closed. This is a very simple two-way handshake, and the point that I mentioned here is that each side independently closes the connection. There is yet another thing you should be aware of, which is the reset packet. Now either side can terminate a connection using this particular reset packet, and this is often triggered by any odd behavior. For example, let's say A and B are 2 nodes. Now Mallory has tried to establish a connection with B pretending to be A. So she said SYN, so basically she spoofed A's IP's address and established a connection with B where she chose some sequence number X. Now B in response to this is going to send a SYNAC. It will choose its own sequence number Z and it is going to acknowledge this particular sequence number. And this will have destination IP as equal to that of A, and as I mentioned earlier, these packets will come to A. Now A doesn't know what this packet is because it did not open a connection to B. So it will wonder what is this, and this is the odd behavior, and immediately it is going to send a reset because it did not open any connection. And this reset, it is going to acknowledge this Z+1, this packet whatever it has received. And as soon as B sees such a reset packet, it is going to abort this particular connection. One other thing to note about reset is immediate. In other words, as soon as B receives a reset packet, it is not going to send acknowledgement saying yes, I am resetting. It will just abort the connection. There is no acknowledgement needed. So one thing to note about this is that such resets can be used to launch denial of service. In other words, if there is a connection between A and B, and Mallory, if she wants to disrupt this connection, rather close this connection, if she were able to assemble a proper reset packet, then she can close this connection and thereby launch a denial of service. In the construction of this reset packet, if you are not careful, B will not accept the reset packet. In order for B to accept this particular reset packet, certain fields have to be properly filled. What are those? So the first thing you should note is that a TCP connection is identified by a 4 tuple. So this corresponds to the source IP, source port, destination IP, and destination port. Only when you fill these values correctly in this reset packet, it will go to the right process on B. So that is something to take care of. In addition to that, there are two other fields within the TCP packet that are of importance. One is the sequence number field and another is the ACK field. So B in general is going to expect packets with sequence numbers within a window. Because TCP is a window-based protocol, this is why it expects packets with sequence numbers within this window. That is why it is important that you choose random sequence numbers so that Mallory cannot figure out what this sequence number is. If it falls outside the window, B will not accept the packet. That is one thing. This ACK packet is acknowledging what packets B is sending. In other words, this refers to the sequence number that B has chosen. And this sequence number here that I talk about refers to the sequence number A has chosen. Now this ACK value is not as important as this sequence number. Even if you choose an ACK value that doesn't fall in the window, depends actually on the implementation, this reset can still work. Some implementations also insist that ACK also fall within the window. Some implementations don't care about it. So depending upon the implementation, whether or not the reset packet will be accepted will be decided by that. But this getting the sequence number correct is very important. So this is what this is saying. Getting the correct sequence number, port IP to get it to the right socket, and correct sequence number so that the TCP will accept this particular reset packet. This is the only check. So with that background on TCP, let's look at attacks. So we will focus on protocol specific attacks here, especially on TCP. Earlier we were covering this eavesdropping, disruption, spoofing. Eavesdropping here does not make sense because it is essentially a lower layer functionality. Disruption and spoofing are possible based on TCP. How to do it? That is what we are going to see next.